Hi. So this talk will be about DNS and specifically all the security you can encounter while doing an audit on a DNS server. So first of all, who am I? Clément Berthaud, working for Synactive. We recruit. So mostly doing pen test as well as reverse engineering and low-level stuff. The context of this talk is we had to do a security evaluation of a well-known DNS server. So an authoritative DNS server. And when you think you know DNS, you come across DNSSEC, NSEC, NSEC3, DDNS, and TSIG. So what the hell is it? First of all, DNS, so everyone knows DNS, like the root of the internet, basically the translation between names, host names, and addresses, but also storing lots of metadata for anti-spam, such as DKIM and all this kind of stuff. Not designed with security in mind, designed with performance, and is kind of old. So no authentication, no integrity, and no encryption. So to solve this problem, the guys who work on that introduced DNSSEC, which is an extension which was introduced in 2004, which provides DNS server authentication. So basically, when you do a request, when you perform a request on a server, it assured you that the server you're talking to is the real one. So the idea was to have the least performance impact possible. So you can't, it's DNS, so it's like very used. So you can't just sign on the fly, it won't work. So deployed on most TLDs nowadays, but almost never deployed among corporate DNS servers. So basically, Google doesn't use DNSSEC in its own. So the ultimate basic overview of DNSSEC. So basically, it had a DNSSEC record in the zone. So in your zone, which your DNS server will serve. And this DNS key record will just store the public key, which will then be used to sign the zone. So when you request, for example, test.example.com, you will have the record you requested, as well as an error SIG record, which contains the signature for this record. So then we have a problem, because you need a proof of non-existence, because if you are an attacker, you can just reply, you are in the man in the middle, and you just reply, oh, this record doesn't exist, and basically it won't work. So the problem is you can't pre-sign the zone for an unknown answer, so they thought about NSEC, which was introduced in 2004, basically in the same time as the DNSSEC. So what it does is it is a pre-signed linked list of the zone domains. So you will have all your records in the zone, which will a linked list will contain all these records, and then it's signed. So basically, when you request a domain name such as blah.example.com, the DNS server will reply, there is no record between app.example.com and c.example.com, and blah is in between. So basically, this response, this answers is signed. So you're sure that the record doesn't exist. So what does it? It allows zone enumeration. So basically, you can just retrieve a.example.com, then c.example.com, then all the record in the zone. So it's pretty bad. So then there are a second attempt to do that, which is NSEC3. So I don't know what was NSEC2, but NSEC3. And it solves this zone enumeration problem by just using SHA-1. So basically, instead of having a.example.com, you have the SHA-1 for this record. So there are projects on GitHub which does walk the zone and then you have a patch for John to crack the hash and retrieve all the zones. So basically, it doesn't work. And then there are lots of additional proof of non-existence in DNSSEC. So there is online sign, white lies, NSEC5, black lies. The NSEC5 is still a draft, I think. So basically, lots of successors to cover this problem. Then there is TSIG. So it's an authentication mechanism which is used as access control for zone transfer, so AXFR, and dynamic zone updates. So basically, it's both used when you have two servers that need to sync, both two DNS servers that need to sync their zone, as well as you are an administrator and you want to update a zone on your server, so you have a client for that. And so the authentication mechanism is based on an hashmark with a pre-shared key. So basically, it's the same key to the two actors, so the server and the client, or the two servers, will use the same pre-shared key to talk and sign their request. So we will come on that later. Described in an RSA from 2000. So it doesn't have any. It's not part of DNSSEC. It doesn't have any link to DNSSEC. So in detail, how it works. So basically, we here have a query, and it adds an additional record, which is TSIG, which contains all the metadata. It's at the end of a query, and then you can see that you specify a key name. So you have to you have to have the right TSIG name. Then an algorithm name, and then you have your MAC, which does need to match all the that's the signature of all the requests with the hashmark with a pre-shared key. So when you send a request which is signed with TSIG to a DNS server, the DNS server has to reply with also an answer which is signed by TSIG with the same key, and so we have the signature here. So the quirks about TSIG is that the answer is signed with the same key, and the digest sent in the request is used to compute the answer, so you can have a matching this is the answer for this request. So what if the digest is invalid, or what if the timestamp is out of the time window? So in the RSA, it said that when the server detects an error relating to the key or MAC, the server should send back an unsigned error message. If an error is detected related to a TSIG validity period, the server should send back a signed error message. So basically, you should do stuff, but we don't know. So the case of IC bind 9, so basically the most used DNS server in the world. So we have a request which is signed with an invalid signature. So the digest is in itself invalid, but also the digest doesn't have a size that matches the algorithm which is used. So basically here we have lots of zeros, and we are supposed to use like hashmark 256. Sorry. So what the hell? Basically, we send a wrong digest with a wrong size. We got a signed back answer. So maybe we can use this later. The same with Knot DNS. So it's another authoritative DNS server which is also very used. So same thing here, but we have an invalid digest, but the timestamp is ahead of time. So basically we have a fudge, which is the default validity period, which is 300 seconds, and so we sign with 301 seconds. So what we can see here is that the answer is, this is the answer of the DNS server. The answer is signed, but we also have an error message. So basically, the two of the most used DNS server doesn't really follow the ERC. So why do we even care? So according to the ERC again, when a server has generated a response to a signed request, it signs the response using these components. So the request MAC, the DNS message, and the TSIG variables. So basically, we control this. This we do not control, but we could manage to make do. This actually we don't care because we don't control that, but it needs to be part of the request, and it won't make a problem. So basically, we have a signature forgery with arbitrary prefix. So how can we exploit that? So the prerequisites, we have a TSIG key name, because as we saw earlier, the TSIG key name needs to be part of the request and needs to be valid. It's part of the metadata which are sent to the server. We have a zone, which is example.com, served by a bind9 instance, and we want to inject some record or edit the DNS zone. So step one, we forge a DNS update packet. So basically, this is a query with an update record. So here I can inject records in the zone example.com, which is a text record. Then we add some padding. So basically, the padding will be used to absorb the DNS message here, which we do not control. So we need a valid DNS request after that. So we remove the padding because it's cool. And then we add the padding with an arbitrary size. So step two, we send a trigger packet with the forge packet as MAC. So basically, we have a MAC which is this size, and the MAC in itself is the data of the request we forged earlier. So step three, so we have a MAC length which is invalid. So as we saw earlier, bind9 will sign its answer. So using first of all, the request digest prefix with its length as a 16-bit unsigned integer, so basically the 2 bytes here. Then the MAC signature. Then the answer data without the TSIG record, which is always the same length. And then the TSIG record without its digest and digest size attributes with the error and other fields. So basically, we had earlier our padding text record, which we can set, which size we can set to the size of this record. And then we will have the signature of the whole forge request. So step 4, we send the forge update request. We patch some stuff because we need to have the additional record count set to 0 because that's how we compute the signature, but that's something else. And we also need to specify the transaction ID to set to the size of the MAC we had here. Basically, because transaction ID are the 2 bytes, the first 2 bytes of the DNS request. So we need to have it so we can have a full valid DNS request here. So time for a demo. We will exploit the vulnerability on bind9 and as said earlier, prerequisite dynamic DNS updates and configure to use TSIG and the name of the TSIG key used. Oh, that's kind of blurry. Is it better? Yeah, seems so. Okay, so we have a bind9 running here, and here is the attacker shell. And I don't know how to press play. Oh. Okay, so first of all, we try to request a record from example.com. So basically, GreHack.example.com. So we have the address 1.2.3.4. So, oh, we can't see anything. So in the exploit script, we want to add the record GreHack, which will add 1.3.7. So, out events. So we executed the script. So with the TSIG key name. So we sent the trigger request, then the forge request. We got the hash MAC, and the DNS zone was updated. So basically, we were able to edit a record from a DNS server without knowing without having the TSIG key. Okay, so vendors' response. Very quick and professional response from both ISC and the CZ.NIC. So that was three vulnerabilities in both bind and not DNS. The patches for bind and not DNS were delivered in a few weeks. And the guys at ISC are working on a new RFC for TSIG, which will be clarifying the shadow zone of the DNS. So props to them. Do you guys have any question?
Thank you. Questions? You do have questions, yes. Was it a question? Yes? No? No, okay. I'd like you to comment on the incredible pleasure to read a few bunch of RFCs and check against against the code in different implementations.
Didn't have much sorry as well.
Do you have any feedback about exploitation of this vulnerability in the wild?
We didn't really try to exploit it in real life, but I don't understood the question actually.
Did you heard about exploitation by attackers on this vulnerability, or any feedback from the community about exploitation in the wild?
I don't think it was exploited in the wild because it's still a laboratory vulnerability, because you kind of have to have the right DNS server configuration. So only you using TSIG, because you can also have an ACL by network IP. And also you need to brute force the DNS key name, which is used by the... Even though it's not supposed to be random, it's supposed to be a name, just not the real key.
Okay, thanks.
Other questions?
Have you any plans of testing other DNS server like DGB DNS or Power DNS?
Actually, we tried NSD and Power DNS. So we reviewed the implementation of TSIG for first two DNS, and it was clean.
Other questions? If not, thanks Clément again.